Okay, let's ride the wave and see if we can convert back and forth between complex and polar form. Okay, again, with the famous find all solutions. Oh my goodness, there'll be 5 of them because I see an x to the 5th power. That's not going to factor, is it? All right, I don't have a special thing for x to the 5th minus 2 to the 5th. So that's not going to factor. So instead, I'll say, hey, let's just find one solution. Let's just take the 5th root and say, aha, 2 to the 5th power is 32. So I know one of my solutions is 2. I put a dot there. And I know there should be 5 solutions. But because of polar coordinates, look at how quickly I can find. Right? I know they are going to be on a circle. The radius is going to be 2. And they're going to be every 72 degrees. How do I know it's 72? 360 degrees divided by 5 is 72 degrees. So I know where my 5 solutions are going to be. They're all going to have a magnitude of 2. The first one's at 0 degrees. And so then I can add 72 degrees, add another 72 degrees, add another 72 degrees. Make it a little bit easier to see the points there. But I've got my 5 solutions. Now, what if I actually want them as complex numbers, right? What if I actually want them in the form a plus bi? I rapidly found all 5 solutions in polar form. How can I convert them? Right? Complex numbers are the form a plus bi. Well, the polar form is r comma theta. So if I have r comma theta, how do I get back to a plus bi? So this example was on a previous slide where I said, hey, let's take a look at the number 4 plus 3i. Figured out that the hypotenuse was going to be 5. That, of course, is the radius of the circle or the magnitude of the vector. And then, of course, we did some SOHCAHTOA and said, hey, tangent is 3 over 4. So arctangent of 3/4 got me that really weird 36.9 degrees. Okay, so now how do I go the other direction? If I know that the polar form is 5, 36.9 degrees, how do I get back to that 4 plus 3i? Okay, so now let's pretend I don't know that the answers there are supposed to be 3 and 4. So I'm going to kind of fade them out a little bit. You can still see them a little bit, but let's pretend we don't know they're 3 and 4. Well, I can label my sides as A, right? Not A for adjacent, but A because that's the real number component. And B because B is the coefficient that goes with that I. Well, I know the cosine of theta is adjacent over hypotenuse. In this case, it's the real number component A over, well, 5, because our hypotenuse here is 5. Now again, I want to make sure I am set for degrees to do anything. But I can figure out a close approximation for the cosine of 36.9 degrees. And of course, I can then multiply that by 5. And I get about 3.998, and it keeps going. Hey, that number is really, really, really close to 4, isn't it? That's how I can backtrack and get that 4. The reason why it's not exactly 4 is that 36.9 degrees was not exact, right? 36.9 degrees was an approximation, rounded off. That's why we're not getting exactly 4. Right? When we did the arctangent of 3/4, we did not have 36.9 exactly. That's the discrepancy. Okay, so indeed, the real number component is 4. The imaginary component. Okay, so now let's start working on the imaginary component. If I want to find the opposite side, I know that the sine of theta is opposite over hypotenuse. Again, make sure that we're in degrees. So the sine of 36.9 degrees is very close to 0.6. And when we multiply that by 5, we get an answer very, very close to 3. And of course, that's what we should have, right? Because we started with 4 plus 3i. So indeed, that opposite side of the triangle should have a value of 3. So if we start with a plus bi, we can find the radius with the square root of a squared plus b squared. And we can find the angle by doing the arctangent of b over a. Again, notice we ignore the number I when we're doing that. If I start with r comma theta, a is just going to be r times cosine theta. B is going to be r times the sine of theta, right? Because each time we ended up doing 5 times the cosine or the sine of that 36.9 degrees, right? We also took the radius, because that's the hypotenuse, and we also ended up multiplying by the cosine or sine of that angle. So if we know r comma theta, that's how we can quickly convert it back to complex number form. So if those are my 5 solutions, I can quickly transform them back. Of course, 2, 0 degrees, I don't need to change at all, right? Cosine of 0 degrees, of course, is 1. So we really do get 2. All right, sine of 0 degrees is 0. So yeah, that really is just plain old 2, right? If I didn't recognize it as just being plain old 2, and I actually tried to work with the r cosine theta and r sine theta, I would have gotten 2 plus 0i, which of course is 2. Of course, that was the first solution. Now let's get a little bit trickier. All right, we've got 4 more solutions we need to look at. So what does 2, 72 degrees turn into? Well, 2 times cosine of 72 degrees gets me about 0.618. 2 times the sine of 72 degrees gets me about 1.902. And so if I want to round those off, I would say, oh, 0.6 plus 1.9i. For the 144 degree angle, hey, notice that we get a negative value for A. But think about where that solution was in the picture, and you say, oh, that's right, we would have gone left, and then we would have gone up. Okay, for 216 degrees, ooh, we went left. Right, here's a picture of the jogger memory of what's going on here. And oh my goodness, we reused a value, didn't we? Look at that negative 1.618. And if you're wondering, well, gee, how come it's getting reused? Well, take a look at where our solutions were. They have the same real number component, right? They have the same value on the horizontal axis, the real number axis. And then, of course, I can go find B. And it's negative because we went down. And hey, look at that. One of the points is 1.176 units above the horizontal axis. The other one is negative 1.176 below. Right? So the same distance above and below that axis. So we're kind of like reusing some numbers here. You can probably predict what's going to happen on this last one. All right, on this last one, it should be very similar to that 2,72 degrees, right? It should have the same real number component because it looks like we went the same distance to the right, but then instead of going up, we went down. So let's see what happens here. Let's multiply this out. Oh my goodness, it's the same horizontal distance. And it's the same vertical distance, but instead of going up, we went down. And so those are our 5 solutions. Okay, so let's try one more of these real quick. X to the 6th power is 729. Well, I can find one solution just by taking the 6th root. Right? 3 to the 6th power is 729. So I've got one solution, right? Use a calculator if you need to. I know that the radius is going to be 3. Now, because there are going to be 6 solutions, right? It was x to the 6th power. I just go every 60 degrees and I'll get a solution. So those are my 6 solutions. Radius has to be 3 for each one. I just keep moving by 60 degrees. And then, of course, if I want to change them to complex form, notice where I snuck that I in there, right? So I go 3 times cosine of 60 degrees will get me the horizontal component. 3 times sine of 60 degrees will get me the vertical component. But then, of course, after I know my vertical component, we got to sneak that I in there. And look at how nicely those work out, or at least the 1.5 worked out nice. Okay, then when I move on to the next one, again, it looks like we're kind of reusing some answers here, right? Because there's a lot of symmetry as we go around the circle. Oh, hey, that's just going to be negative 3. Probably should have figured that out without touching a calculator, right? Because it's 180 degrees away from our first answer. Hey, how about that? Reusing some numbers again. Of course, pushing buttons on a calculator. And say, oh my goodness, And those are my 6 answers in complex form. Okay, so we're looking at, ooh, a flowery worksheet. Look at that. But then our background image, instead of being flowers, it's an ocean wave on a sandy beach. Okay, so let's get to work.